Okay, so for number one, we're looking for which segment the car moves the greatest distance. Because we have a velocity versus time graph, that's going to be our area under the curve. So if you look and break it down between each of these sections and just look at the area down to the x-axis, these are all positive, this one is negative, and the greatest area would be this chunk right here from A to B. Which of the following is true about the motion? It says that the cart is at rest from B to C. If you look at B to C, this is a velocity graph, so it has a velocity of 8, which cannot be at rest. Your velocity would have to be 0 to be at rest. The average acceleration from A to B is less than the average acceleration from C to D. That one, let's say a question mark, and we'll come back to it, see if there's any easier ones to cross off. C, the cart is slowing down from D to E. So from D to E, the velocity goes from 0 to -2 to -4. So the graph itself might be going down, but because this is negative, it's actually getting faster and faster just in the negative direction because it's getting farther away from the 0 meters per second. So it is not slowing down. It's actually speeding up just in the negative direction. And the cart's position at point C, or I guess time C, is the same as the cart's position at E. So if you look, in this case, it is moving forward, slowing down. In this case, it's moving backwards, speeding up. So it's possible that this could be moving forward and going backwards and end at the same position. We'd have to actually calculate how far it's moved in order to see if that is true. So we're going to calculate the area under the graph for both sections. This one, base times height, this would have a base, I think this is going back to 0.2. Yeah, so it would have a base of 0.4, height of 8 divided by 2 gives me 1.6. This one, base of 0.246, height of -4 divided by 2 gives me an area of -1.2. So if you go 1.6 meters forward and 1.2 meters backwards, you do not end at the same spot, so it is not D. That makes the answer B. And the reason your acceleration on average is less in this section than this section actually has nothing to do with the curve, the fact that it's getting flatter. The average would be like, if it was constant, on average, the acceleration would look something like this. And if you look at these two lines, this one is steeper. Remember, the slope of a velocity versus time graph is the acceleration, so a steeper slope means a greater acceleration. Less steep means less acceleration. You also can think about both of these change their velocity by 8, whereas this one takes more time to change that velocity than this one. So even though they're changing the same amount of velocity, it takes this one longer, so it must be changing at a lesser rate. So its acceleration is less than the average acceleration CD. This graph shows velocity as a function of time for a 4-kilogram object traveling along a straight line. Graph has 3 different segments, A, B, and C. For the entire time, there's an applied force of FA1. In the second section, there is now a frictional force. And in section C, the friction force is taken away, but now there's a second applied force, FA2. First, it's just asking about displacement, so we can do our quick calculations. Area of this under the curve in this section would be 2. This one would be 2, and this one would be 1. So then the area for the displacement for A and B are equal to each other, and the displacement for C is less. So you can cross off these. It says these two are equal and C is less, and they were all positive velocities, so all moving forwards are all positive displacement, not less than 0, so C was our answer. How does the friction force in B compare to the applied force? Well, I have the applied force the entire time, and in B I now have a friction force. In B, it says that it's moving at a constant velocity. If it's moving at a constant velocity, that means the forces are balanced, so the friction force has to be equal to the applied force. Number 5, how does the applied force introduced in section C compare to the applied force acting on the object the entire time? So in part A, it has just the applied force 1. In part C, we took away that we introduced the friction in B, but then took it away. So in C, I still have the applied force 1, but I now have the second applied force. And because the object is slowing down, whereas with just the applied force it was speeding up, that means that this force must be greater, FA2. Because if I had this force and it was speeding up, let's say it was going to the right, I don't know, just positive direction, I was gaining in velocity. If I'm now slowing down, that means I have a greater force against me. So we can cross off A and B because we know that A2 must be greater than A1. And then by how much, we have to actually look at the numbers. So if we were to calculate the acceleration in both of these, that would tell me about the net force in each of them. So for A, the acceleration is 2 in 2 seconds, so acceleration of 1. 2 divided by 2 is 1, not 2. And then C, it changes by 2 in 1 second, so it's an acceleration of -2, which makes sense. The negative sign because the greater force is in the negative direction. So I can use this to find my net force very easily because net force is mass, which was 4 times acceleration. So this one has a net force of, 4 times 1 is 4. And then this one has a net force of -8. So if the only force acting on it is FA1 and has a net force of 4, that means that the FA1 is 4. And if I know the FA1 and the net force is -8, that means this one must be -12. So that means it is more than twice as great, so D, FA2 is more than twice of FA1. What is the object's change in kinetic energy in section A? Well, change in kinetic energy is just subtracting the kinetic energy from start to finish. So the starting kinetic energy in section A, well, your velocity was 0, so this would be starting with 0 kinetic energy. Kinetic energy at the end is just 1/2 mass of 4, velocity squared. That's going to give me kinetic energy of 8. So then if I end with 8 and I start with 0, then my change in kinetic energy would just be 8. It's gaining 8 joules of kinetic energy. In section B, what is the change in kinetic energy? There is no change in kinetic energy because it's staying at a constant velocity. That means the kinetic energy, which depends on velocity, is not changing. If there was no friction in section B, what would the change in kinetic be? So if I have my section A that goes like this, in section B, what happened was we introduced friction, so it kept going at a constant velocity, but I'm saying, what if I take away that friction? What would be the change now? Well, still section B is from 2 to 3 seconds. If you take away the friction, then it's just going to continue to accelerate at the same rate that it was accelerating, which was an acceleration of 1. So after 3 seconds, your velocity would now be 3. So I'm going from 2 to 3 meters per second, and I want to know how much kinetic energy that changed by. So I find this ending kinetic energy and the starting kinetic energy. We already found the starting, so it was the end of section A. You get 8, and then this one at the end you have 18. So if it goes from 8 to 18, that means that the change in kinetic energy is just the difference. So it gains 10 joules. For number 7, we have a small cart going at a constant acceleration of 2 in the positive x direction. At t equals 0, the cart has a velocity of 8 in the negative x direction. So I have my acceleration is positive 2, and that's constant, it won't be changing. And then I have a velocity of -8, but the velocity will be changing because there's an acceleration. That's just the velocity at t equals 0, or v naught, the starting velocity. I want to know what's happening at t equals 3 seconds. So first of all, I know that at any point I have a positive acceleration. So if you have a positive acceleration, let's say like positive is to the right, if you're moving to the right, then that must be speeding up. If instead you're moving to the left, that velocity to the left, that means that you are slowing down. So to move to the right and slow down is actually impossible because your acceleration, or move in the positive direction and slow down, is impossible because if it's moving to the right, then you would have the same direction to be speeding up. So A, no matter what way it's moving, that wouldn't make sense. Moving in the positive direction and speeding up could be okay. Moving in the negative direction and slowing down, yes, if my velocity was in the negative direction and A is positive, because it said it was positive, that would be slowing down, that's okay. And if it was moving in the negative, it could not speed up because it would need negative acceleration to speed up. So without calculating or figuring out which way it's moving, we can automatically cross off A and D just based on knowing a positive acceleration. So at 3 seconds, I need to know, is it moving in the positive or negative directions? That's basically asking, do you have positive or negative velocity at 3 seconds? So we can use v equals v naught plus at to find the velocity after 3 seconds. So negative a plus acceleration of 2 times 3, that's 6, so that gives me -2. that means I have a negative velocity and I still have a positive acceleration, so it must be moving in the negative direction and slowing down. Because these are opposite, slowing down and moving in the negative just means negative velocity. Same situation, but now I'm asking after 4 seconds. So let's plug in and see what the velocity after 4 seconds is. If you plug in exactly 4, you're going to get velocity is 0, but I'm not asking at 4 seconds, I'm asking more, so let's just plug in 5, and that gives me positive 2. So that means I now have a positive velocity. I still have the positive acceleration from before, so if it's positive velocity, it's moving in the positive direction. Same direction means it's speeding up, so F. Ball A is dropped from rest, and at the same instant, ball B is shot horizontally from the same height. Which one takes the longest time? They would take the exact same amount of time because the Y component is what determines the time it takes to fall down. Going faster to the side is not going to make it fall down any faster. And the greatest speed hitting the ground would be B because both of them are going to hit with the same Y velocity, but then this one also has a greater X, so has a greater total velocity. Or you can think about energy. This one starts with just potential. This starts with the same potential and kinetic, so at the end it'll have more energy, more kinetic. Number 9, we have a rough horizontal floor. It says constant speed, which means that the forces are balanced. Careful, balanced forces doesn't mean that this has to equal P or that N equals F, because I have more than one force in some of these directions, and some of these forces are at an angle, so I need to break it down. So for the P, let's break that down into P, this would be P sine and P cosine of the angle. And then I still have the normal force up, and I've got the weight force down, and I have friction this way. So I know that these two add up to the weight. So if I have a force up, that means my normal plus that Y part equals my weight, so the normal has to be less than the weight. So normal less than the weight, we can actually cross off everything. A is the only one that says normal is less than the weight. And then the reason that P has to be greater than F is that P cosine of the angle is equal to F because they're balanced. So if only part of this force equals this force, this must be a greater force because only part of it makes up this. At number 10, we've got a 20 Newton force, and the coefficient of friction is 3, so we can find the force of friction. It'd be mu Fn, which gives me 12. So that means that my net force is 8 newtons to the right, which means that your acceleration is to the right. And it says it was moving to the right because I forgot to change these answer choices. So you could have crossed off those immediately. If it's moving to the right and the acceleration is to the right, that means it must be speeding up. We are looking at this angle. If you decrease the angle, now you're pulling it more to the side and less up. So then your normal force would have to increase, because you're not pulling up as much, because before you were holding up some of that weight. If you pull it more to the side, you're not holding up as much weight, so the table would have to go back to making up for that force. And the acceleration, well, if it's frictionless, you're now just adding more force to the side, so your acceleration would also increase because you have a greater force in the direction that it's accelerating. Sliding down, frictionless. And we are looking for free body diagram. So force gravity would go straight down. Normal force would have to be perpendicular to the surface, so it would be at this angle. And then there's no friction, so those are the only two. So D. What would the free body look like if it was moving up? And I meant to say with friction, so my bad. Hopefully I said that in class. Now it's going to be the same friction, or not the same friction, the same normal and the same gravity force straight down and at an angle. If it's moving upwards, then your force of friction would go opposite to the direction of motion. It would be down along this ramp. I'll draw it right here. It's probably easier to see. So this would be the answer for the next part. If F12 is the box of force that box 1 exerts on 2, and F21, and I meant to switch these, is the force that box 2 exerts on box 1, and W1 is the weight of box 1, we want to rank the 3 forces from greatest to least in these situations. So we can't do it without knowing the situation because it depends on which way it's accelerating. So if the elevator is moving up and getting slower, that means the acceleration is in the opposite direction, which means that your net force or your acceleration is directed down, so your net force would have to be down. If it is moving down and getting slower, that means our acceleration is the opposite direction, so then that means your net force would have to be up. If it's moving up and getting faster, that means acceleration in the same direction, so your net force would have to be up. If it's moving down and getting faster, these would be in the same direction, so your net force would be directed downwards. So now we have to look at our individual forces. So by definition, the force that 1 exerts on 2 and the force that 2 exerts on 1, these have to be the same, because that's Newton's third law, equal and opposite forces. Remember, we described it as the force of A on B is the same as B on A. If it's the same two objects, their force on each other has to be the same. So F12 is going to be equal to F21 no matter what the situation. So we can go ahead and put these in all of them. 2. Now, how the weight compares is going to change for each of them, depending on which way it's accelerating. So it's easiest to think about drawing a free body diagram of the 1 block, because we have the weight 1, which obviously would point down, and then the normal force comes from box 2, so that's just the force of 2 on 1. Now these two would only be equal if it was at rest or at a constant velocity. I have that these are all accelerating, so if it is accelerating down, like in this first example, if it's accelerating down, then that means weight 1 has to be the greater force, and this one has to be smaller. So these two would be greater than the weight, so weight 1 is smaller than these two, which are equal. And that's going to be the same in this case, because it doesn't matter which way it's moving. I just care the acceleration. And if the acceleration is down, I have a greater force down, which means weight 1 is greater. I just did that wrong. Good thing I just got that. So this is going down, which means your greater force is, or it's accelerating down, which means your greater force is down, so W1 would have to be greater. Yes. This would be less than the weight. Now, in these two examples, when your acceleration is up, that means you have a greater force up, so this one would have to be the greater force, meaning this one is the lesser force. So then these two are greater, and less than that is weight 1. There we go. It's just deciding which way it accelerates, so that tells me which force is bigger. If it accelerates down, this one's bigger. If it accelerates up, then this one's bigger. Block of mass m is at rest. Give an expression for the coefficient of static friction in terms of m, theta, and g. So this is Fg normal, and then if it's just at rest, it wants to slide down, so the friction would have to be the opposite direction. And something you just need to memorize instead of trying to break down this angle on your own and figuring out where the angle goes, etc. Across from the normal force is the force of gravity cosine of the angle. And this one is Fg sine of the angle, and then still force of friction. If it's at rest, that means that everything is balanced, so my force of friction is equal to Fg sine of the angle, and my normal force is equal to Fg cosine of the angle. You can find Fg by multiplying mass times gravity. And we are looking for coefficient of static friction. Well, friction is just mu Fn, so I can replace this with mu. And Fn, we just said, was mg cosine of the angle equals mg sine of the angle. Just bringing this down. Divide the m's, they cancel. Divide the g's, they cancel. Divide cosine over. And you can leave it as cosine, or sine over cosine. Or you can say, oh, sine over cosine. That's just tangent. And that's the right answer. The block is now sliding down the slide, give an expression for the acceleration in terms of these things that we have been given. So super similar right here, super similar to right here. The only difference is that now they aren't balanced. There's going to be acceleration. The acceleration is in this direction. So the net force is going to be the Fg sine of the angle minus the friction force, because friction will be working against that gravity force. Mg sine of the angle minus force of friction, we just said was mu Fn, and Fn was mg cosine of the angle. Fnet is mass times acceleration, so to get A by itself, you just divide the mass over. So you have g sine of the angle minus mu g cosine of the angle. And that would be the acceleration of the object. A person of mass m stands on a scale. For each one, we're going to choose what the scale reads. Does it read equal to the weight, more than the weight, or less than the weight? So if it's going at a constant speed, that means that everything is balanced. We can say it's just equal to the weight, so those two are easy. And then whether the scale would read more or less than the weight just depends on which way it's accelerating. So let's think through our two options. So we could have the weight mg. I could have the normal force greater than mg, or I could have the normal force less than mg. In this case, the acceleration is up. In this case, the acceleration is down, because which is the greater force? So now we just need to figure out which way is it accelerating. That'll tell me which one it is. If the elevator is moving up with decreasing speed, that means slowing down, so it goes the opposite direction. That would be acceleration is down. If acceleration is down, that means your normal force is less than your weight, so that is A, between 0 and mg, or less than mg. If the elevator is moving down with decreasing speed, means it's slowing, so that would be opposite direction. That would be acceleration is up, which means that your normal force, or what the scale reads, is more than the weight, so greater than mg. If it is moving up with increasing speed, velocity would be up and acceleration would be in the same direction because it's getting faster. So acceleration up, we just said, was c, greater normal force than weight. And if it's moving down and increasing speed means getting faster, so in the same direction, acceleration is down, your normal force would be less than the weight, so between between 0 and mg. 16, at the highest point, the velocity and the acceleration. Well, acceleration is to the center, and because it's going clockwise, your velocity would just be to the left. These make a right angle, so is B. Ball of mass M is fastened to a string and swung in a vertical circle. At the highest point, you would have both tension and you would have the force of gravity. So the two of those together would give you your net force, and the net force for something moving in a circle is just called the centripetal force. Centripetal is mv squared over r, tension plus mg, so you would just subtract this over, mv squared over r minus mg. You'll notice it doesn't have it in terms of mv squared over r, it has in terms of mac, which is fine because centripetal force is v squared over r, so you can just call this ac. So mac minus mg would be my tension, so c. In a popular music park ride, the cylinder is set in rotation, the floor drops away, and they are suspended, meaning not moving. Well, they're moving sideways, but up and down they're not moving. And we have a coefficient, a radius, and we're looking for velocity. So first we need to figure out our forces. So we've got the force of gravity, obviously. And the thing that's holding it up is not the normal, because nothing is pushing it up. What's holding it up is the force of friction, because it's parallel to the surface and keeping it from moving. And the normal force, the direction the surface is pushing on the person, is actually into the center. And because he's hanging, we know that these two are balanced, so the force of friction is equal to mg, or mg, and then force of friction is mu Fn. Well, that means we need to find the Fn. Fn is not equal to the force of gravity. It's our normal, or it's our centripetal force, because the force is pointing into the center. So my centripetal is my normal force, which means that my normal force is mv squared over r. So I have mu mv squared over r equals mg. M's cancel, trying to get v by itself, multiply the r up, divide mu over, and then take the square root. So square root of gr over mu. Planet X has twice the Earth's mass and 3 times the Earth's radius, because we're looking at gravitational field strength, the gm over r squared. If I have a factor of 2 over 3 squared, that is 2/9 the gravitational field strength of the Earth. Well, the Earth's is 10, so 2/9 of 10 gives me roughly 2. So 2.222, so close enough to be 2. Gravitational field strength is 2g. If it has half the mass, then what would you have to do to the radius in